So hello everyone, this is lecture 42 for the mathematical physics. In the last lecture we have completed the Cauchy integral theorem, Cauchy integral formula, Cauchy integral means derivative formula. We have completed all the formula related to Cauchy. Okay, and we have seen all the examples related to that. Okay, so from today onwards we will start the Taylor series expansion. So before starting the Taylor expansion, let me tell you what is the power series, because Taylor expansion is nothing but a power series itself. So every analytic function can be represented by the power series. So any fz analytic function can be expressed in the form of a series, and that series is called the power series. How you write the power series? A power series in powers of z minus z naught n is a series of the form this. So this kind of form is called the power series an z minus z naught to the power n, where an is some constants, it can be real or complex constants, and z naught is the center of the series, means where along which you are expanding, and n is the power. So series will be like this, and n will go to infinity. So this kind of form of any function is called the power series, and any function which is analytic can be expressed in this form. So let's see. Where z is a complex variable, a0, a1, a2 and an are complex or real constants called coefficients of the series, and z0 is complex or real called as the center of the series. So we call this z0 as the center of the series. We will see what is the meaning of the center. Okay, so here just the definitions are here. There are special cases when z not equal to 0, means we take the center as 0 most of the time. Then we will get the series as a0 plus a1 z plus a2 z square plus and so on. Okay. So what happens? Normally a series with variable terms will converge for some z and diverge for others. What is the meaning of convergence and divergence? See, if a series for a particular values gives the same value as fz directly, so we say that complete series converges to a point. Okay, or if in some reason there are some values of z, for that the series converge, means gives a single point. Okay, so then we call that it is convergent to a particular region. Okay, so it can be converged to a particular point, it can converge to a particular plane, and it can diverge means the function will tends to infinity, means series will go to infinity, means it won't give you a single value. So that is the meaning of divergence. So the power series can converge in disk with center z naught, means there is a center and there is a disk of radius r. Then the whole series can converge in this point, in this region, means all the points in this region are valid, means it will give you a same value as fz. So that's why we call that region as, means a disk where this series is convergent, and it can converge to a simple in whole complex plane, means in whole complex plane the series is convergent, means it will give you the same value as fz what the series is given. Okay, so it can be converged to a disk particular radius, it can converge to a whole plane of complex, and it can converge at a single point only, means at the center only, means other than that point it will diverge. So that's how this power series can converge or diverge. Let's see some example. You are very much familiar with this kind of function. This is a geometric progression. We know in the r means ar and minus 1 there is terms ar square ar cube. That kind of form is geometric progression, where you take the common ratio, and the sum will be ar and minus 1 divided by r minus 1. So if that common ratio is less than 1, then you take this function as a 1 upon 1 minus z. Okay, means here it is your a. So this is nothing but geometric progression, you know about it. So this can be expressed in this kind of series 1 plus z square plus z cube. This is nothing but z upon 1 will give you common ratio z square divided by z will give you common ratio z. So if mod z is less than 1, then this series to infinite will converge to this function. Okay, so only for this reason, where this mod z is less than 1, so it will give you a disk of center z naught, that is 0. So this is an example of where power series converge to a disk. Okay, for mod z greater than 1, this series will diverge. Okay, you can check that it will tends to infinity greater than 1. For less than 1, it will converge to this disk. So any point lying in this side, this series will be converged. Okay, and will give you the same values. Now this was the example where series is converging to a disk. Let's see an example, another example. So if function is exponential z, so we know its series can be written in this form. Exponential series can be written in this form, z to the power n divided by n factorial. So 1 plus z square divided by 2 factorial plus z cube by 3 factorial. So this is the expansion of this. Let's see where it is convergent, where it is divergent. So we can check it by the ratio test. What is ratio test? You have to take means a term and its previous terms. So a n plus 1 divided by a n we will take here. So for n plus 1 it will be z n plus 1 divided by n plus 1 factorial divided by z n divided by n factorial. Now this will cancel out, means n plus 1 n will give you, means n will cancel out, so you will get n plus 1, and zn z, so zn will cancel out, you will get mod z. Now see, as n tends to infinity, this whole term tends to 0, so this will converge for any z, means it is whether z can be anything here, but if n tends to infinity, this whole will tends to 0, so we will say that this is convergent at all z, means for all z. So that's why it is convergent for whole complex plane. So this is the example where the series is converged to whole complex plane, means at any z it will be convergent. Now let's see where it is convergent to a single point only. So this is our series, so it can be written like this form. Now see, let's check do the ratio test again. So n plus 1 zn plus 1 divided by n zn. So this will give you n plus 1 here, and zn will cancel out, you will get z only. So this will be your this. Now as n tends to infinity, this whole value tends to infinity, so means it is diverging, but for a single value. When mod z equal to 0, it will give 0, so it is convergent for a single value at z equal to 0, otherwise it will be diverged. So that's how you can check that if any series is convergent to a single point or a whole plane or a particular disk of region. Now if there is disk, then you can find the radius. See, from here you can see that if it is convergent for all z, then radius of convergence will be infinite, means in whole region it will give you the complete region. And if there is particular fixed radius, then it will give you a disk, and if it is radius equal to 0, then it will give you a single point. So you just can calculate the radius of convergence, then you can see if this is, means these conditions are verified, means it will be very easy after finding the radius of convergence. So let's see how to find the radius of convergence. Consider a smaller circle with center z0 that includes all the points at which a given power series is convergent. Okay, so that circle z minus z0 equal to r, it can be represented by this form. So r is radius of circle, and this is a circle of convergence, and r is radius of convergence. So convergence within the circle z minus z0 less than r, so means the convergence region will be this open disk. For z minus z0 greater than r, it will diverge, we know that, I already told you. For r tends to infinity, it means convergent in whole complex plane, because r is tending to infinity. R equal to 0, convergent at one point only, and r is not equal to 0, convergence within circular disk. So I already told you these things. Now we will see how to find this radius. That will be very great milestone. So let's say we have this series an z minus z0 to the power n. This is power series. For any power series, we can find the radius of convergence by using this formula. Limit n tends to infinity, an divided by an plus 1. These are the only coefficients we are taking of this, okay, for the power series. So this solving this limit will give us the radius of convergence. Let's see some examples. First of all, let's take this zn. So you know what is the expansion of this? It will be z1, z square, z3. For all that, coefficients are 1 only. So an and an plus 1 both are 1. Now see, this limit will give us 1 here. Now radius you have is 1. So, and center is taken as 0. So it will be mod z equal to 1. So mod z less than 1 will be your radius of convergence. And we know that for this series, we have mod z less than 1 as the radius of convergence, because greater than this, it will tends to diverge. From here we can check, from greater than 1 it will diverge. So this should be the condition, and we are getting the same condition, means this formula is correct. Okay, let's see some other function. Zn divided by n factorial. Now radius of convergence will be an divided by an plus 1. So 1 upon n factorial divided by 1 upon n plus 1 factorial. This will give you n plus 1. Now for n tends to infinity, this whole term will tends to infinity, means radius of convergence is infinity, because this value is radius. So this function is convergent in whole complex plane. So this was the same result we were getting here. Now let's see this third one. This is nothing. So n factorial Zn. Now limit n tends to infinity. So it will be n factorial divided by n plus 1 factorial. It will give you n plus 1. Then this will cancel out. So 1 upon n plus 1. Now as n tends to infinity, this will tends to 0. So this is radius. So the radius equal to 0. Means convergent at z not equal to 0 only. So it will convergent at the center of the circle. So this is the same condition we were getting here. So means this formula is very much valid. So remember this formula, very helpful from the exam point of view. Now let's take one more example. Find radius of convergence of power series this. So here our an is this 2n factorial divided by n factorial square. So let's take an divided by n plus 1. So it will give you this 2n divided by n factorial square divided by n plus 1 means 2n plus 2 means it will be 2n plus 1. So it will give you 2n plus 2 factorial divided by n plus 1 factorial square. That will go to the numerator. Now 2n plus 2, 2n plus 1, then this will cancel out. So you will get these two terms here. And same here, the n plus 1 and both factorial square. So n factorial square will cancel out. You will get n plus 1 square. Okay. So now you have n plus 1 square, 2n plus 2 and 2n plus 1. Let's write it. Expand this n plus 1 square here. So you will get this form. Now take the n square common. You will get 1 plus 1 upon n square plus 2 over n. And this term here also take n square common. Now putting n equal to infinity. So you will get 0 here, 0 here, 0 here. So it will be 1 upon 4. Now you are getting radius as 1 upon 4. So the disk where it is less than 1 upon 4, that radius, and center is z minus, means 3 iota is your center. It was given. From here you can check the center is 3 iota. So this will be your reason now, means center will be at 0, 3 means 3 the y. So and radius is 1 upon 4. So you will get a circle. So that is your reason where this function is or this series is convergent. Okay, because you have the radius. So that's how you can find. Now let's see the Taylor series. Well, Taylor series is nothing but just a power series expansion. Okay, so for an analytic function, what is it? If we want to expand analytic function, any analytic function we want to expand, let's say its center is at this z0, and the first point where it is non-analytic is at z1. So any region less than this function will be analytic here. Now see, we can expand this in this region. Any function can be expanded in this region. So what we are getting in the previous, these are the series. Now we can find these series, okay, very easily using the Taylor series expansion. So it is convergent in this region. So let's say we need to find a series which is convergent. So how can we find that series? So that is the actually formula for Taylor series. So we want to expand analytic function fz about z equal to z0, and let where z1 is the first point where this function is non-analytic. So we'll take the inside this region, and we want to expand the r function in this region. This is analytic region. So we want to expand analytic function fz about z equal to z0, and let z1 is the nearest point where fz is non-analytic. Then z dash is this point. Okay, so z dash minus z0 is less than z minus z1 minus z0. Okay, so this is less than, then this fz must be analytic on c. C is this. So this is the first one where it is non-analytic. So in this region it will be analytic. So we want to expand the function in this region. So let's say how we can find. So Taylor series expansion formula is nothing but this. Fz can be written as from n equal to 0 to infinity. Fn z0, this is nothing but differentiation of nth order. This is n factorial z minus z0 n. So we know how to find this differentiation using the Cauchy integrals derivative formula. Cauchy derivative formula. So you remember this formula, fn z0 n factorial divided by 2 pi iota f z dash dz dash z dash minus z0 n plus 1. So you can use this formula to find the derivative or the integral, but we can do the direct here from. Means let's say find the series. So it will be for 0 to infinity. So it will be f z0, means 0 means first normal function, then 1 means first order derivative. So f z0, 0 will be 1 here, so it will be 0. So first term will be this, 1 will give you this, second will give you second order derivative, and this, and so on. So this will be your Taylor series. And if you put z0 equal to 0 here, then you will get whatever series you are getting is called the Maclaurin series for z not equal to 0. That is special case when you take the center at 0. Okay, so this is the Taylor expansion, and remember this formula. This is very helpful to expand any function. You can expand any function which is analytic. Okay, so let's take some example. Let's take the same example. Let's see if we get the series which we were talking about or discussing so much. So fz is 1 upon 1 minus z, and center is given as z not equal to 0. So we need to find the series for this. So we need to find the first order derivative. It will be 1 upon 1 minus z square, and f dash 0, because this is z naught is 0, so it will be 1, and here also f0 will be 1, f double dash z will be this, and at 0 it will be 2, f triple z will be this, 3 into 2 it will be 6. Okay, so f triple dash 0 will give you 6. Now you have all the terms. Let's just put them here. So f z naught you have, f dash z naught you have, and z naught is 0. So let's put in the, substitute the values. So fz will be 1 plus 1 upon 1 factorial z, 2 over 2 factorial z square, plus 6 over 3 factorial z cube, and it will go on. Now see, this will cancel out 1, this will cancel out to give you z cube. So this is the same series we were talking about, means now the sum of this series will be 1 upon 1 minus z. So same we can find for the, means see, this is the same result we were talking here. So this was this. So you are getting the same expansion using the Taylor. So that's how we can say that Taylor expansion is very much valid. So for z not equal to 1, now center is iota. So how you can find? There's the same results now, but this time z naught will be iota. Substitute in place of z naught, that will be 1 upon 1 minus iota. F dash iota will be 1 upon 1 minus iota square. F double dash will be this. So you can find the fz, the same, just substituting the values in this series. So you will get 1 upon minus 1 minus iota, 1 upon 1 minus iota, z minus iota, plus 1 upon 1 minus iota cube, z minus iota whole square, plus, and go on, so on. Now see, you can write this in the form of general terms. So for n equal to 0 to infinity, this is 1 upon 1 minus iota n plus 1, z minus iota n. Now let's re-verify what we were talking about, the radius of convergence. So let's see, for this expansion, what is the, for this series, what is the radius of convergence? Okay, means up to which region this series is valid and convergent, after which it will become divergent. So how you can find that? So you will use the radius formula, radius of convergence. That is nothing but an over an plus 1. So this is your an. So 1 upon 1 minus iota n plus 1 divided by 1 upon 1 minus iota n plus 2. From here you will get the value, this 1 minus iota mod of this, and it will give you mod root 2, means mod of 1 minus iota will be root 2. So center is iota, so z minus iota should be less than root 2. So you will get a circle where center is at iota, x0, y1, and radius will be root 2. So that region is, means this series is convergent in that region only. So that's how you can check this. Now these are the very important results which you need to remember. You will use them in the many questions and the exams. So find the expansion for exponential z, cos z, sin z, cos hyperbolic z, sin hyperbolic z for center at 0. So try to find them using the same formula we were talking, Taylor expansion formula here, and you will do it yourself. In next lecture I will give you the solutions, but up to then try them by yourself. Okay, that's it. Thank you everyone.